So basically what this presentation is about is what I've seen people do to make systems work a bit, be a bit more cost effective to install and work more efficiently, basically to look at getting the payback, simple payback down, getting the return on investment a bit better. Because 99.9% of the clients I've ever run into that's their main concern is, am I going to save enough money to make this feasible to build? So it's really boils down to that. What I've tried to do here is basically looking at what you can do to help show a client that it is more feasible, or what they could do to improve the feasibility of a system. Looking at trying to show how it's feasible, or what they like, different kinds of things that can be done, is to try and help them understand how you can do this better with their help in a lot of cases. So what this kind of graph basically is set up so that the bigger this area is, the more feasible it is. You could do it whichever way you like, but basically looking at the geology, looking at the integrated design process. You've got an architect or a client that is willing to participate really effectively in an integrated design process. Take your recommendations once you've got the energy model built, how you can change the building or how you can do things to the building to make it better. Looking at what kind of contractor resources you've got available. That you sometimes don't have a lot of control over. There may be, if you're in an area where people haven't done a lot of geothermal systems before, a lot of contractors are hesitant to install pipes in the ground for whatever reason. This is a whole bunch of nonsense, for example, is the kind of thinking that goes with this kind of technology to some extent. And if you've got a contractor that's willing to work with you and find more cost-effective ways to get the pipe in the ground, then it can be more feasible. Utility costs, again, you don't have a whole lot of control over what the utility costs are. There's fixed costs that the utilities have to deal with, and in order to stay in business, they have to deal with them. Site accessibility, sometimes you can get onto a site to get a ground heat exchanger in easily. Other places, pretty tough. I have seen systems put into existing buildings, under the building, and there are people that have developed drill rigs that can fit into a fairly low ceiling space and can get the pipe in the ground. But again, you're looking at a fairly expensive process in most cases. So you got to make the most of the drilling that you are getting done in that kind of situation. Then you have to look at other kind of considerations that the client may have. We've had a client, for example, that several times during the feasibility process, I can sell the cachet of geothermal. He is developing a shopping center, and to his clients, feedback he'd had from his prospective tenants is that, yeah, they can buy into that. Want to be a green development. And those kinds of things can make a difference on how feasible it is in client's eyes. So looking at on a specific project, this is on a project in Australia, actually in a fairly hot climate. Got about 15 acres of land that they've got to play with. They're looking at putting in about 167,000 square feet of commercial office space, 13,000 square feet of retail space, and 600,000 square feet of apartments. So fairly about 800,000 square feet altogether. And looking at the, what's part of the integrated design process, there's a number of things that can help increase the score on this point, basically. Looking at if you've got a client that's willing to work with you on getting the best glass for that kind of a situation to help balance the loads, rather than simply saying he wants blue glass or green glass or whatever. He gets the right kind of glass. I don't care if it's blue or gray or green, as long as it helps us balance the building loads a bit better. That's going to help. If they're willing to work with you on that, then that makes the project, is going to help make the project a bit more feasible. And again, working with, now the only way you can really determine if that's going to be more feasible is to work through the whole process with an accurate energy model, using the energy model to show what the impact is as you make the changes. And again, it's once you've got the geometry of the building entered into most of that software, whether it's DLD, or whether it's Train Trace, or whether it's IES, or Design Builder, or Energy Plus, once you've got the geometry entered into that software, it's not that difficult in most cases to change the type of glass you got in, change the shading factor, change the U value, or whatever else. And you can see the results of that relatively quickly. And then you can model what that does to the ground heat exchanger design. You can see the impact of that fairly quickly. Hard part is getting the grunt work of the geometry into the system. One of the problems I've seen, tell me if I'm wrong, is that in most engineering firms, most architectural firms, who's the guy that does the energy modeling? Newest guy on the street. That's right. For the most part, like it's grunt work. There's no maybes about it. It's time consuming, it's tedious. Nobody wants to do it, but it's probably the one most important thing that you can do on optimizing a ground heat exchanger design. You have to know what the energy loads are. And often it's just the guy that's fresh out of university. He's been tasked with getting the geometry of the building, and he doesn't know a whole bunch more about building construction or systems than your neighbor's cat does at that point. So realistically, at least the energy model should be reviewed, and even that can be fairly time consuming and tedious. On you're looking at a 150,000 square foot building, that can be fairly time consuming. But it's probably the one most important aspect of designing a ground heat exchanger. Looking at the internal gains from lighting and electrical equipment. Every watt you can cut off of that is energy that you don't end up putting in the ground. Most commercial buildings, we've got buildings in Winnipeg where it does hit -40 that are cooling dominant. They dump more energy into the ground than they pull out of the ground. One of the things that exaggerates that to some extent is that fact that the electricity used to run the compressor has to go somewhere, and pumping energy has to go somewhere. When you're cooling a building, that energy is going into the ground. So you take your cooling loads and multiply it by about 1.1 and a quarter or so, and that's about what your loads to the ground really are. When you're extracting energy from the ground, when you're heating the building, the compressor loads actually help heat the building. So about 2/3 or 3/4 of the energy heating your building comes from the ground. So that right away unbalances the system a little bit. Even if the loads are exactly equal over the year, they're unbalanced as soon as you add a compressor to it. Pumping costs. So ideally, you want to try and look at cooling loads that are actually about the same or a little less than the heating loads. If you can get to that point, then the system will run forever and ever and ever. And whether in some cases you don't have any choice but to put a fluid cooler in or a cooling tower in to augment or basically create an artificial heating load to get rid of energy. Again, working with the electrical engineering firm or whatever that's specifying the lighting. Again, it's not always easy. LED lighting is becoming more cost-effective all the time, so it's getting easier. But a couple of years ago, it was virtually impossible to convince a client or an electrical engineer that there could be a payback on LED lighting. You're not going to get it just on the savings on running the lighting alone. Once you consider what it does to the size of the condenser, and even with the conventional system, the size of the cooling tower. But with the ground loop, that's a bigger deal because the ground loop is a lot more expensive than the cooling tower. So if you can get buy-in from the design team, that's going to make the project more feasible to build. What we found in that one building with three different components, the commercial, retail, and residential, the loads were a lot different. Retail, no cooling or no heating loads whatsoever. It's only a fairly small component, but the cooling loads are absolute. There was no heating load on that site. Commercial space, again, very little heating load, very little domestic hot water load, and the residential was was even off balance by quite a bit as well, and this isn't even considering the compressor loads. Once you added the domestic hot water loads, then all of a sudden that changed the picture, at least on the residential side. 800 apartments, there's a lot of people that are going to use domestic hot water for showers in the morning, for washing dishes and clothes and whatever else. That added a lot of heating load to the system. So ideally, look at whatever you can to try and balance the loads. Then what that did to the overall total project loads was move the heating load up a lot and didn't increase the cooling load. So instead of dumping heat into the ground loop, if you can dump it into domestic hot water or a swimming pool or a snow melt or anything you can use, that's a bonus. Looking at the total borehole length required for the different options, looking at just the freestanding ground heat exchangers, you're looking at individual ground heat exchangers for each of these separate components. It worked out about 440,000 feet of drilling. Looking at what happened if you simply added the domestic hot water load, that dropped it down from down to about 370,000 feet of drilling. That knocked a lot just by adding the domestic hot water load. You're benefiting the client. His domestic hot water is going to be less expensive to make, and at the same time you're reducing the cost of the ground quite a bit. So looking at, once you looked at putting a common ground heat exchanger, simply by taking these loads and putting all three buildings on the same ground heat exchanger, reduced the loads quite a bit. Adding the domestic hot water loads, looking at just those simple options without changing the building at all, just how you designed the ground heat exchanger and what was all connected to it. That reduced the ground heat exchanger size by 26%. That's a fairly big deal. 110,000, 111,000 feet of drilling at probably 20 bucks a foot, 30 bucks a foot. That can make it more feasible. Yep. Yeah, for the most part. Commercial building, if it's an office building, probably not going to be a lot of hot water load unless there's something, schools would be a big deal. It can be. Yep. Yeah. The other thing you've got to design for the if you work with how the equipment is designed to operate, what you'll find is that the temperature lift is a big deal. You've got and what I mean by temperature lift is the difference between the heat source, the ground loop, and the heat sink, the building. For example, if you're producing, if you've designed a system that the ground loop in the winter is going to get down to, let's say, 40 degrees, and you're needing 120 degree water because that's what your air handlers are going to require to deliver the BTUs that you need, you've got an 80 degree temperature lift. Okay? That heat pump is going to run at a COP, that's or the COP is this line right here, the dotted line. It's going to run at a COP of less than 3. Taking exactly that same heat pump, changing the temperature parameters, if you designed your ground loop a little bit bigger, and it's going to run at, let's say, 45 degrees, and you've designed the air handler to work with 95 degree water, you've only got a 50 temperature lift. Now all of a sudden that same heat pump has a COP well over 4.5. That's a big deal. Exactly the same heat pump. The other thing that happens is you've got a little bit more heating capacity and a little bit more cooling capacity out of exactly that same heat pump. Heating capacity, cooling capacity 63,000 here and 80,000 here. You've got an extra, what is that, 25% or whatever it is. And same in the heating capacity, 100,000 versus 104. It's not a huge deal, but the efficiency of the system, you're going to use a lot less electricity to deliver a few more BTUs. 19% better on the cooling capacity, 4% on the heating capacity. Efficiency is up 50%. Like that kind of thing, looking at those kinds of details is going to help make the system a lot more cost effective and more palatable to the owner. And then looking at the heat pump efficiency, looking at just simply the efficiency of the heat pumps that you're selecting to put in there. And I've seen this happen more often than not, where a contractor comes and say, I can put in these heat pumps, they're cheaper, so it's more cost effective. Well, once you look at what that does to the cost of the ground loop, because you've got more compressor energy going into the ground, if the building is cooling dominant and you've got a less efficient heat pump, you're putting more compressor energy into the ground. Okay? So what that means is your ground loop is actually going to get bigger. So we're looking at 6,600 feet of drilling in this case. And that's 20 or 30 bucks a foot. That's a big deal. Have any of you done any work with thermally activated building systems at all? Thermally activated building systems uses the mass of the building to store energy. And radiant floor cooling, radiant floor heating. And there's a building in Winnipeg, actually in Manitoba Hydro built a building about 500,000 square feet. Whole building is thermally activated building system. You've got radiant floor heating and cooling throughout the building. They cool the building with about 66 degree water, heat the building with about 78 degree water. And when you think about what that does to the efficiency of the system, that's a big deal. Yeah. You've got to deal with the moisture on there for sure. And I think what they've got is a small dedicated chiller just for specifically to get the chilled water cold enough to get rid of the moisture. And in our climate, basically in winter, that's not a problem. We've got fairly cold, dry air. That's pretty easy. Summer, they got to deal with it more. But basically, they'll put the piping in concrete walls, the floor, pillars, even whatever else. And what that does basically is if you've got a cooling peak load of, let's say, 100 tons at 3 o'clock in the afternoon, you can absorb an awful lot of energy when you've got a great big, huge mass of concrete that can absorb a lot of energy. Temperature might go up a degree or two, but if you're relying just on the air system in the system, it's going to go up a lot quicker. It'll absorb a lot of the heat energy simply into there, and it'll carry you through the peak cooling loads or the peak heating loads. And you can actually reduce your equipment capacity by anywhere between 15 and up to 30%, depending on how much mass you're working with, type of building, and that kind of thing. Radiant floor heating and cooling, and you basically take advantage of there's ways of modeling the building. I think probably Transys is probably one way of doing it. It gets a bit more complex in the modeling, but some of the pipe manufacturers such as Uponor or Rayhow will certainly work with you on that. But the thermal activated building system, it can be a big deal. It really, what it does a couple of things. One, it makes the heat pumps work more efficiently. So you've got a bit more capacity out of the same heat pumps. And it also actually lowers the heating and cooling peak loads. So it does a couple of things on there. Energy storage. Energy storage is a wonderful thing in a whole bunch of ways. Taking advantage of the energy storage in the ground, but you can also take advantage of the energy storage externally with the mechanical system, ice storage tanks or hot water tanks. And where they work well is where you've got peak loads that are predictable and intermittent. A data center wouldn't be a good application because you've got cooling loads basically continuous. But if you bought a retail store, when they open the doors and turn the lights on and let people in, that's when you get the cooling loads. Before that, you got no cooling loads. Office buildings, the same thing. Schools, the same thing. And reducing, and it does a couple things. One is that it actually reduces the peak rejection to the ground. And it can help you take advantage. So it reduces the size of the ground heat exchanger, so it reduces capital cost. And if you happen to have time of use rates available, that's a bonus. The numbers that I've been seeing on kinds of systems that if you're using the heat pump capacity, for example, that store in Denver has got 350 tons of equipment in it. That's all it has. It's got about a 530-ton cooling load in real life, but 225 tons of that comes from the capacity of the ice storage tanks that are built into the system. Nighttime, there's very little cooling load. They make ice all night, and then during the day they have the 350 tons of equipment running. When they can't keep up, not if they can't keep up, when they can't keep up, then the ice supplements. So domestic hot water loads are also generally, in a lot of cases, are predictable and they're intermittent. 6, 7 o'clock in the morning. How many, like everybody here probably, or most of you probably had a shower first thing this morning? You're not showering right now. That happens before you head out to a conference or to work or to school or whatever. It's very predictable that you're going to have a large hot water demand between 6 and 8 in the morning. And you can have another smaller peak in the afternoon when people come home and start making dinner and washing dishes and whatever else, doing laundry. And that's predictable. Every day, or most days, that's where it is. And if you've done the hourly, hour-by-hour energy model, you can look at it on a daily basis. You see exactly where the peaks are going to be on cooling, and you can look at get a good estimate of what the heating loads are going to be for domestic hot water. So reducing peak heat rejection with a thermal activated building system, ice or chilled water system, and domestic hot water storage tanks drop the size of the ground loop by 60,000 feet. Now we're down to about 250,000 feet. Simply by looking at energy storage. Looking at the mechanical system design, if the design team has got an open mind towards looking at thermally activated building system, for example, rather than a forced air system, then that is going to help make the building more feasible. It's probably a little bit more expensive. I haven't got any good numbers on it. There's a fellow in Australia that I'm doing some work with that is getting actual quotes. He's designed 2 systems for the same building. One's an air system, one's a thermally activated building system. And he's going to get some pretty accurate costs in Australia. It might be different here, be different in the UK or whatever. But what I'm interested in is that I know for sure it's going to reduce the size of the ground loop. Heating and cooling loads are going to be smaller, and that's going to reduce the size of the ground loop. That's the whole point of the exercise. Like if you've got a design team that's willing to work with you on this kind of stuff, and they're not always, but if you can show them on an energy model that if you change the glass from this to this, this is what happens to the size and the cost of the ground loop. And then the contractor resources. In this particular site, there's not a lot of geothermal heat pump system work that has been done in Australia. This project is Australia, but we did find one of the contractors there that does a lot of foundation work. Hadn't done geothermal system work, but what they do is install what they call wick drains. You've got really soupy, sandy, silty, soft clay soil. What they do is try and drain that by inserting paths for water to drain into the aquifer below that. Drain the land a bit, and they do it in the U.S. as well. And they've got this mass is about 75 feet high. They can get them up to about 100 feet high, and they can shove a U-tube in a matter of about 5 or 10 minutes. And they actually tested it. They were willing to work with us. In that case, we didn't have a contractor that had done geothermal system installation, but we found one that was willing to work with us and test a few things out, test thermal conductivity, and they could sort of, in 15 minutes, they could insert an 85-foot U-tube in. So then you design a ground loop based on 85 feet. So, and drill in Perth, Western Australia happens to be an area that does a lot of resource extraction, minerals and gold and whatever else, and things get expensive. Compared to the rest of Australia, probably about 15-20% more expensive everything. Coffee at Starbucks is 15% more. And that goes on through the wages, everything. And drilling costs were about, I think about $70 or $80 a meter. So not more than that, over $100 a meter. So about 30 some odd bucks a foot. And that's just the drilling. That's not even getting a pipe in the ground or grouting it. So anything that we could do to reduce the capital cost, looking at working with different kinds of contractors that you might not think of otherwise, that can help make the system more cost effective. Basically, really soft silt clay, sand, that kind of stuff. If you've got boulders in there, probably not so much. But they can install. I talked to one guy out of Denver. This company out of Denver does the same kind of thing. They can put in up to about 15,000 feet of drilling or YouTube a day, which is a big deal. If you've got the right conditions. If you're going into granite, it's not going to happen. But if you're in a river delta, for example, I suspect probably the mouth of the Mississippi in that area is probably like that. Silt, sand, clay, that kind of stuff would be suitable. There's probably other areas, but again, it might be site specific. But if you can find that kind of a contractor that's willing to work with you, that can make it a lot more feasible. Looking at the mechanical system, if right now in North America, I don't think there's a lot of tab systems going in. There's not a lot of contractors, not a lot of designers that have done a lot of work with it. It's quite common in Europe. I know a couple folks in the UK that do a lot of this, and it would be, again, if you're asking a contractor to do something that they're not familiar with, guess what? There's a bit of a fear factor there, and rightly so. Haven't done it before. They know that there's going to be a learning process, and they're not sure what to expect, so they're going to allow an extra 10, 15, 20%. But once they get used to it, it becomes more common. They get more used to it and be able to do it. Same with ice storage tanks. Ice storage tanks have been around a long time. Actually built in New Jersey, these particular ones. But again, a lot of contractors aren't used to working with this kind of system. Most contractors are not familiar with it. So there's a bit more hand-holding that needs to go on all the way through it. But it can make the system a lot more cost-effective to build. Again, looking at working with the mechanical contractors and that, if you've got the contractor resources, you've got the contractors on side with you, it becomes more feasible. Utility costs. Again, that's something you don't have a whole lot of control over. In this case, this project was done in a fairly hot climate. Ground temperature is over 70 degrees. The domestic hot water loads were on the project, without the hot water, without adding the domestic hot water loads, which were going to be heated by gas otherwise. That can be taken away and help reduce the cost. Add more benefit to the client. They're not going to have to pay for the gas to heat the hot water. They're getting it basically for free. And then if you add the thermal storage tanks to go with it, that kind of thing, that can help. And they're looking at what their cost of natural gas there is about equivalent of about 12.25 cents per kilowatt hour, which is a lot more than here right now. Here, so I think it's about 3 or 4 cents per kilowatt hour roughly. Their electricity costs in Australia, they got some interesting rates. 44 cents on peak during between 8 and 10, 8 in the morning, 10 at night. And at night time, there's still 15 cents. So there's pretty good incentive to try and get rid of this. So taking advantage of the utility rates, if you just did a conventional HVAC system, gas and domestic hot water, this is the kind of information that the client really needs to understand. Here's what the cooling peak load is, and looking at how much cooling we could do off peak, just conventional, don't worry about the energy storage or anything like that. A ground coupled heat pump system by itself will help reduce the peak cooling loads. Western Farmers Equipment Co-op has done some studies, drops it by about 0.6 kilowatts per ton. So that kind of thing is going to help. Just putting a conventional forced air geothermal system in there, water to air heat. putting in a water-to-water heat pump system with a thermally activated building system makes the heat pumps even more efficient and gives them better capacity. And then it allows you to reduce the peak loads simply because you've got taking advantage of the thermal storage of the building itself, in the building mass itself. And then taking advantage of the ice and the domestic hot water storage reduces the peaks a lot further. What that does to the energy cost, conventional standard ground source heat pump with water to air heat pumps, that's not bad. Roughly 30% reduction. That's not uncommon. But take advantage of the electricity rate structure that they've got there with activated building system and with ice storage and domestic hot water storage, doubles that saving. That's what the client is going to see. Yep. This was done on a feasibility study basis, and talked to a lot of people at Upanor, and they've done a lot of systems like that here. Talked to a guy out of Germany for quite a bit, and what they've been finding is that they reduce the peak loads by about 15 to 30%, even more. This was modeled at about a 20% saving. I think the only one that I've heard of that can probably model that accurately is Transys, which is just about as user-friendly as a rattlesnake. Transys. It's I haven't used it. I don't think it's a very user-friendly kind of program, but it will model this kind of stuff. It's got the math built into it that you can do that. Yeah. Yeah, right now there's no easy way of modeling that that I'm aware of. Again, some of the guys with some of the people with some of the suppliers will help you with the modeling. And again, there's going to be some cost attached to that. But if you can spend an extra 10 or 20,000 bucks on the modeling on a couple 100,000 square foot building and save 200 grand on the cost of the ground loop, that may be worth looking at. You can get some idea at this point. And during the feasibility study, we looked at, okay, conservatively, we can probably save 20% based on kind of construction that they were talking about. At this point, during the feasibility study, they had the footprint of the building. They knew that it was going to be concrete construction, but that's about the extent of it. So at this point, you have to do during the feasibility stage. You're doing some guessing, but again, you've got to do the research to back that up, make sure that. Yep. They want cheap, right? In this case, for sure. Yeah. 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 And you're seeing more and more smart meters being introduced all the time and that kind of thing. So I think we're going to see a lot more of this kind of stuff. Energy modeling is going to get better. I've heard that AutoCAD is working on their version of yeah. Yeah, there's people that are working on better software. I know I've talked a lot to some of the folks that do the ground heat exchanger design modeling and software and that, and they've got some interesting things coming up over the next while. They're open to working with designers on how to make their software work better for them. And the energy modeling software there's no question about it. It's not terribly user-friendly for the most part, but it's probably the most important thing but it is good enough right now and user-friendly enough where you get a guy that does a fair bit of it that can model a building, a couple 100,000 square feet in a matter of a week and a half. So there's cost to it. But if you can build that cost into the cost of the feasibility study, what we'll often do is work with, give a client a 2 or 3 phase proposal for the feasibility study and design of a system. And we'll give them an option to bow out of this proposal at each step along the way. First, we'll do the feasibility study. That might cost you $10,000 size of the building. Do the thermal conductivity test. At that point, you can make a decision whether you want to go forward or not. Do the thermal conductivity test if you want to go forward, and we'll confirm that the assumptions that we made are reasonably accurate. And then if that still looks promising, then you can go ahead with the design of the system. That might be another $60,000. Then at that point, we have enough knowledge about the geology site so that we know we can place the test borehole where it needs to be placed so you can use it when it's done, and that it's at the depth that's most appropriate for that site. Okay, utility costs. Again, if you're looking at things like time of use rates that you can take advantage of it, that kind of thing can make the system more feasible. In this case, it did. Is the site accessible? Can you get drill rigs on the site, or can you get the kind of equipment you need on the site? They've got about 15 acres of land, and the buildings cover about 15% of it. We had about 12.5 acres to play with where the ground heat exchanger is done. So looked at horizontal directional drilling in this area, and the deeper wick where there's the installation with the wick drains, using that, design the system accordingly. The other thing that we had available on that particular site was an aquifer that we could take some advantage of. If you've got a site like this, these kind of big sewer lines can make it a bit more challenging to put a ground loop in. Site construction logistics can be a pain in the rear end. And we've had one project in Toronto where we actually had to move the ground heat exchanger field over probably about 20 yards, simply because that's where they were going to park their site trailers. And they weren't willing to change, the contractors weren't willing to change that. So you do what you got to do. If the site is large enough, you can, sometimes you simply have to go under, if it's not large enough, you may have to go under the building. I haven't seen a lot of this kind of work done where you've got the ground loops in the piles, and I've got pretty mixed feelings about it, the logistics involved in that. There's one project that I saw in Calgary where they actually tried to do the geothermal piles, and they lost about 15% of the boreholes simply because instead of pumping the concrete to the bottom of the pile hole with a trimming line like they should have been, they just dumped it into the top, and that just wrecked half the pipes on. So that kind of logistics, like, I'm not convinced that geothermal piles are cost effective. Do they work? Sure they do. They're done right. Are they guessing they're probably more expensive simply drilling between the piles? Okay, so unless you've got contractors that are willing to work with you properly. But again, you've got to get your pipe attached to the steel cages that they're putting in the piles when they need to put them in the holes. So there's a lot of logistics involved that are going to have an impact on cost. If you happen to be near a body of water, you can certainly take advantage of that by putting plate exchangers or building plastic pipe exchangers and putting it in the lake or the ocean. Got that kind of thing available, then site accessibility, there's different factors that you've got to look for. If the only option you have is drilling under the building, that would lower that score, site accessibility. In some areas, some other considerations that need to be thought about sometimes is areas like California, for example, where they've had the drought for the last number of years. Using cooling towers is not the most popular thing in the world because they simply don't have the water in some areas to be able to just evaporate it. And if you can avoid that, then that can keep the utility on board. Other considerations that I've seen, you've probably got some of that happening here is when it's coming into Albany. One of the guys that was sitting beside me was working with a bank in Albany that is doing green financing. That was his job. He hasn't done a geothermal system yet, but I'm seeing more and more of that kind of thing happening where you get private companies owning and operating the ground heat exchange. You get a client that they will pay for the installation of the design and installation of a ground loop and own it for 20 years and lease it to them or run it like a utility. Is different models that can be done. And we did a system, a district system for a town in north of Vancouver, where the town owns the geothermal utility. They invested in the cost of putting the pipe in the ground. The developer installed the piping down the streets, and the homeowners connected up to it just like they would with a gas line. And that kind of thing is starting to happen. Ball State University, that they've got a whole campus system. This one's got, what, half a dozen or so buildings connected to it. That's happening more and more. Whether it's financed by the owner or that's financed by somebody else, that kind of model can certainly help make it more feasible. Capital cost is a big deal. If you can work with financing agents to do that, whether it's a bank or a utility or whatever, that can make it more feasible. You can get heat pumps that will produce water up to about 150, 160 degrees Fahrenheit. They're not terribly efficient at those temperatures. Ball State University, I think, is running at about 140 or 150 degrees. They've got two central plants, and they're distributing hot and chilled water. Another way, the system that was done in north of Vancouver on the district system, we're not heating the water with it. What we're doing is just connecting all of the different buildings up to a common ground loop. They happen to have a hockey arena that the town owns, and when the development gets big enough, they'll put a water-cooled condenser on the refrigeration plant, dump that heat into the ground loop, and then the houses will take advantage of that instead of building more ground loop. That's the kind of thing you can take advantage of. Other considerations, I've seen more and more of this kind of stuff. Eco-friendly, environmentally sensitive, looking at, and they were looking at a green project and selling it as that. And I've seen that more and more. So those kinds of things can make it more feasible for the owner or developer to look at doing geothermal systems. What's happened in Toronto over the last 5 or 6 years is there's one or two developers that started doing geothermal systems, differentiate themselves from all of the other developers. They call themselves the green, marketing these green projects. And within about 2 or 3 years, 3 or 4 other developers started doing the same thing, just to keep up. And they're doing it just as a matter of course now. That's what they do. They want a geothermal system. And then government policies sometimes can have a big influence on whether, for example, several cities have required that buildings meet certain LEED standards, or Manitoba, for example, has a policy that any building that gets government funding, whether it's a community hall or a hospital or whatever, they have to meet LEED Silver, plus they need an additional 30% energy points. And the only way most of them can do that is with geothermal. So that kind of thing, government policies really help. And again, one of the things an association like NY-GEO can do, and is doing, from what I understand, working with the politicians, policymakers, to help make this work better. And that's certainly going to make the projects a lot more feasible. One of the things that we had about on the geology on this site, that's one of the other things that we've looked at that can make a project more feasible. This particular site, they've got about 90 feet of really soft silty clay. Then they've got a layer of confining clay. And then they've got an aquifer that's fairly good. So but they didn't have enough water available on that particular site to do the full load. They've got about 800,000 square feet of building, probably about 1,000 tons, give or take. And they didn't have enough water. We needed about 1,500, 2,000 gallons of water per minute to run that system by itself. But you can do an awful lot if you've got even 100 gallons a minute, take the peaks off. And the other thing that is really important is that you can take energy from here and cool off this ground loop. So in other words, you can allow the temperature in the ground loop to creep up during the day because it's not large enough to meet the full loads but it can handle it for 6 or 8 hours, and then you've got 12 or 16 or 18 hours at night, cool it off again for the next day. That kind of thing can. And again, looking at getting these kinds of pipes in the ground with this kind of equipment, that varies from one place to the other. This geology favored this kind of a way of getting the pipe in the ground. Horizontal drilling, we looked at an area over here that they was going to be difficult if they were to connect these boreholes that were drilled over here to these buildings that have been long pipe runs. But by running a horizontal bore there and back, it would put all the headers at this end of the field. So it was simpler and more cost effective to do that. And then integrating the well system with the wells here could supply, we figured, about 200 to 400 gallons per minute. And this is based on 300 gallons a minute, looking at about a 9-degree temperature difference in and out of the wells. It would chop the peak cooling loads. Here's the peak without the after the well system was integrated. Here's what the peak would have been without that. So we chopped a lot of the peak off with only 300 gallons a minute. To try and do it with just the wells would have required about 1,500 to 2,000 gallons a minute. So we're only supplying maybe 15, 20% of the capacity we need with the wells, but it can do an awful lot of the energy load because it can run 24/7. Cost of the wells about $180,000 bucks. It's still a lot more cost effective than trying to put a lot more pipe in the ground. And looking at the summary of the changes, starting out at about 450 or just 430,000 feet of drilling. And by the time we got down to about 400 gallons a minute, if we had that available, we'd drop it down to about 100,000. So it's about a 75% reduction in the size and the cost of the ground. So that's kind of what I mean by optimizing the system, looking at the different options. What can you do on that site with that specific building? One of the problems with the geothermal system, these are very site-specific kind of projects. The geology is going to be different from one site to another. The buildings are going to act differently. Same building in Perth is going to be different than the same building here. So looking at all of these different things, trying to push these out as much as we can looking at all those different kinds of things can certainly help make the project more feasible. Again, looking at this design methodology, how you can get it. You're developing basically what you're doing at this point here during the feasibility study. You actually have to create a basis of design. You have to understand what kind of system you're gonna work towards. What's the best on that specific building, on that specific site. So by the time you get to this point, you've already done the basic design of the system. Now all you have to do is get the detailed design and communicate it to the contractors. So you're doing more work up front before the owner even has the information they need to give you the go-ahead. That's one of the big differences in designing a geosystem versus a conventional HVAC system. Any questions, thoughts, comments? Yep. The water there was very shallow, and in Perth, on that area, they've got very specific rules. You cannot much to that water there, period. So again, we looked at that. Yep. And that's going to happen in a lot of cases with surface water systems. That's the first thing I looked at. It's right beside the water. This is going to be easy. Well, not so much. Sometimes it is, sometimes it isn't. But good question.